This talk has to be short, so much of the thinking that went into it is hidden. I have therefore included a list of references and notes with the written version. The things that I am talking about are a patchwork of fragments that are a part of a larger understanding of the Earth system, and because of this, I feel I must frame what I am saying with a warning about the future. 50 years ago, the Apollo missions had reached the moon and shown us the Earth as a blue, cloud-coiled ball of sunlit half-darkness, hung in an infinite void, and an engineer, economist, mathematician wrote a computer program to model all the possible futures of a technological civilization in a finite world. His students published the results as the limits to growth. The backstory of these people is not widely known, but it should be. In 1973, when The Limits to Growth was published, the authors found that it was possible for our civilization to choose to follow a path that led to stability. 10 years later, when they published their first 10-yearly update to The Limits to Growth, they found that the collapse of our civilization is unavoidable, so that now the only question left to answer is something like, how should we live with grace in a dying world? I did not have an answer then, and do not have one now, but I think that asking that question creates a space for constructive thinking. I still hope that if we are lucky, and if we can work together, as we have never worked together before, we can prevent the collapse of our civilization, and with it, the great loss of life that will follow. Or at worst, leave some of the staggering richness of the earth intact in the ruin we leave, and that some people will live to tell stories, and to dance, and to watch their children become adults with delight. Since this is a talk about the Earth system, it is necessary to include some outline information about the carbon cycles and stores that humans have been altering. The size of some of these pools and fluxes are known with reasonable accuracy. Others are estimates, though estimates made on the basis of careful thought and a century's work by climatologists, geologists, oceanographers, and biologists. In order not to interrupt a talk that is essentially about seaweed, I have put these figures in an appendix. Now I will talk about seaweed. Seaweed, macroalgae, are thousands of species of marine algae, and it was not until the mid-20th century that the distribution and abundance of seaweeds began to be mapped in detail. I will ignore this definition occasionally and include other marine algae in this talk because of the very large part they play in the Earth system. It makes very little sense to think about any plant or animal in isolation. All of them are tangled in relationships that seem strange beyond strange. John Muir wrote, "When we try to pick out anything by itself, we find that it is bound fast by 1,000 invisible cords that cannot be broken to everything in the universe. But it seems to me that even this does not begin to capture the strangeness of the relationships that tangle and bind ecosystems in balance." In The Blind Watchmaker, Richard Dawkins wrote about how living things are created without conscious design. He was inverting an argument made by William Paley in 1802 for the existence of a creating deity. While that analogy is useful for thinking about individuals, the relationships between species in ecosystems are frequently so unexpected that I think it more useful to imagine them being assembled by a dreaming, blind watchmaker. The ecosystem the first people of the coast from Baja California to Alaska knew contained kelp forests, sea otters, orcas, grey whales, salmon, sea urchins, and Stella's sea cows. Then Russians came, and with the help of the Aleut, hunted the sea otter almost to extinction for their pelts. Sea otters eat sea urchins, which eat kelp. So with nearly all of the sea otters gone, the sea urchins proliferated and ate the kelp. And that loss of kelp is thought to be the primary cause of the extinction of Stella's sea cow, which lived in the sea around the Kamandorski Islands. When sea otters were finally protected in 1911 and began to control the numbers of sea urchins again, the kelp forest slowly regrew. It is as if we had been removing cogs at random from the blind watchmaker's watch for centuries without understanding how the watch works, and were then puzzled when the watch stopped. But we also hunted the grey whales, which migrate between Baja California and Alaska. As their numbers were reduced, the number of sea otters also fell. It took a while for ecologists to find out how the kelp forest, grey whales, and sea otters were connected. In an undisturbed food web, in a watch with all its cogs, orca hunt grey whales, but as the number of whales fell, the orca were forced to find another food source and started hunting sea otters. So in a repeat of the first catastrophe, with fewer sea otters to control their numbers, the sea urchins proliferated again and ate the kelp faster than it could regrow, and the kelp forests began to thin. These recent examples of the unintended effects of exploiting an ecosystem without understanding it, and the resulting extinction of Stella's sea cow, show how deliberate and accidental modification of habitat can lead to extinction. It seems likely that similar processes were factors in the extinction of the megafauna that occurred as humans migrated out of Africa and spread throughout the world. For the last few million years, the Earth has been cold, with only short, warmer interglacials, and life has adapted to the cold, so that the sudden warming caused by humans burning fossil fuels is now stressing ecosystems. A heat wave along the coast of California in 2013 almost wiped out the sunflower sea star, the main predator of sea urchins, resulting, just as the hunting of sea otters did, in a 95% reduction in the area of kelp forests. This matters because kelp forests, like terrestrial forests, capture carbon dioxide, slowing down the rate of global warming, and they, like terrestrial forests, provide habitat for marine life, so that without them the fisheries we depend on for food and work crumble. I suspect that events like the ones that occurred along the Pacific coast of the Americas must have also taken place along the Atlantic coasts of Europe during the years before records were kept and ecological understanding existed, so that now we live in an altered environment with no memory of its former richness. Seaweed and sediments are a carbon store and sink. It's only during the last few decades that we have begun to accurately measure the global fluxes and stores of carbon. The size of global carbon pools are approximately 38,200 gigatons of carbon stored in the oceans in the form of bicarbonate and carbonate ions. 2,700 gigatons of carbon is stored in soils. 875 gigatons of carbon is stored in the atmosphere in 2014. 580 gigatons of carbon is stored in all living organisms. 10,000 years of agriculture has reduced the global store of soil carbon by 116 gigatons. Annual emissions from fossil fuel burning are roughly 9.88 gigatons of carbon. Annual emissions from land use change are roughly 1.51 gigatons of carbon. Some of this CO2 is absorbed by the ocean and by plants, slowing down very slightly the rate at which the concentration of CO2 in the atmosphere is increasing. Chris Jensen estimates that macroalgae sequester about 0.173 gigatons of carbon per year. About 90% of this sequestration occurs through export to the deep sea, the rest through burial in coastal sediments. This estimate exceeds that for carbon sequestered in angiosperm-based coastal habitats. This is small compared to anthropogenic carbon emissions, but it goes on year after year, millennia after millennia, so that after 1,000 years, macroalgae will sequester 173 gigatons of carbon. Merle is at least 3 species of slow-growing coralline algae that grow in loose beds of fragmented nodules in the sublittoral zone. Merle contains 32% of calcium carbonate and 3% of magnesium carbonate. By dry weight, it accumulates in deep beds over millennia and hence results in the sequestration of carbon on a geological timescale. Merle is also, like kelp, a habitat. Think of forests. If the trees are felled, then all of the life that belongs with them is extinguished. In Europe, it is dredged from the sea floor and used as a soil conditioner. This destroys a vital habitat and a carbon store. The slow growth of Merle means that there is no possibility of this growth keeping up with the losses due to dredging. The ancient practice of extracting Merle from beaches and later by dredging centuries before it was known that it forms a habitat for other marine life is an example of a traditional practice that, because it is traditional, is thought of as honourable, so that it is difficult to stop for the common good. Graal and Hall Spencer write, today, Breton Merle is extracted at about 500,000 tonnes per year and is used in a variety of industrial processes, including agriculture, water purification, mineralization, and the manufacture of cosmetics. They go on to say, Merle extraction in Brittany is now under the control of the French mining management scheme, with quota schemes, for example, 80,000 tonnes on the Glennon Bank in 2001, and regular environmental surveys. However, such quotas are not compatible with regeneration of the resource. The situation is akin to harvesting peat on land where removal far exceeds production. Dredging Merle is like driving a bulldozer through a cathedral to collect the splintered wood of the pews to use as firewood. Do not underestimate the power of tradition to literally terraform the planet. See, for example, the discussion of the choice of a marker for the start of the Anthropocene. One suggestion is that we use the rise in methane caused by rice farming, which began 5,000 years ago. It is thought that this may have prevented the reglaciation of the Earth. A digression to think about phytoplankton. These are not our macroalgae, but they are photosynthesizing algae. Marine phytoplankton perform half of the global photosynthetic CO2 fixation, a net primary production of about 50 gigatons of carbon per year, and half of all oxygen production, despite amounting to only 1% of global plant biomass. Coccolithophores, a component of the phytoplankton alga, and coccoliths, the shells of the coccolithophores, are the main component of chalk. Chalk was formed in the Cretaceous between 99 and 65 million years ago. It was deposited on extensive continental shelves at depths between 100 and 600 meters during a time of non-seasonal, likely arid climate that reduced the amount of erosion from nearby exposed rock. The lack of nearby erosion explains the high purity of chalk. The coccolithophores, foraminifera, and other microscopic organisms from which the chalk came, mostly form low magnesium calcite skeletons. So the sediments were already in the form of highly stable low magnesium calcite when deposited. Coccolithophores are of concern to those studying climate change because as ocean acidity increases, they may begin to have difficulty forming their shells in the more acid water so that the size of the carbon sink they create decreases. I made a very rough estimate of the total global mass of chalk and find that it is at least an order of magnitude more than the mass of the present day Earth's atmosphere. Back to macroalgae and seaweed farming. The total global production of seaweed was about 28.5 million tons in 2014. 5.7 million tons of this was harvested annually from natural beds. In 2014, the annual production of Asian Pacific seaweed aquaculture beds surpassed 2.6 million tons by dry weight. There was a nice article in the New Scientist in 2004 about Kathleen Drew, who figured out how to propagate nori, the seaweed, the Japanese farm. She never knew what she had done because she died in 1957, at the age of 56. But the nori growers knew how much they owed her. On 14th of July 1963, they unveiled a polished granite memorial bearing the likeness of the woman they call the Mother of the Sea, and they have been back to pay their respects and bring offerings of seaweed every year since. It's a lovely story. I've given you a reference. It's worth finding and reading. All farming consumes energy and emits carbon dioxide as an almost inevitable result of constructing and operating a farm, as does transporting the crop to market. This is because the boats, engines, even if they're electric, and the tools the farm uses are constructed from materials that took energy to mine, smelt, transport, and manufacture. Their use also consumes further energy. I grew up in a culture that attempts to solve its problems by constructing machines. And while some of these machines have transformed our well-being, think about sewing machines and washing machines and electricity. The thoughtless use of machinery and energy has allowed us to sleepwalk into a trap. We must now start to find ways to do more with less, and only what we must do, acting only when we must act. In doing this, we must design sustainable agroecological systems. Know that third world farmers, most of whom are women, feed a large proportion of humanity, and in doing so manage to harvest 100 times more edible food energy than they burn as calories in planting, growing, and harvesting. They are therefore 5,000 times more efficient at feeding people than intensive agriculture is, and do so without using much or any fossil fuel. With that warning in mind, Nyat et al. Have calculated that ocean afforestation, farming kelp in 9% of the ocean, would produce 12 billion tons of biomethane as fuel, and that when this is burned, 34 billion tons of carbon could be captured from the combustion exhaust and buried. The growing kelp would capture 53.2 billion tons of carbon dioxide per year from the atmosphere, quickly reducing atmospheric CO2 concentration to a pre-industrial level. They also state that such a large area of kelp forest, if it is possible at a feasible energy and resource cost, would result in an increase in fish stocks. To be fair to the authors, I think they're exploring an upper limit to what might be possible and are not advocating such a large scheme. However, the problem with this scheme, and many others like it, is that it takes no account of the energy and material costs needed to create and operate the scheme, or of the unintended damage that would follow if such a scheme could be constructed. The Earth is not infinite, and we do not have an infinite supply of energy. And while 9% sounds like a small number, 9% of the area of the Earth's oceans is equal to 80% of the area of the North Atlantic, 3 times the area of the USA, twice the area of Russia, and 4 times the area of Brazil. So I'm sure that such a large scheme could not be constructed and maintained. We do not yet know if carbon capture on the scale envisioned by the authors is possible, nor do we know how efficient it will be, nor do we know its energy cost. And even if only a small percentage of this kelp was grown on ropes, I am sure that the entanglement would drive the great whales to extinction. The trouble is that all these schemes are frequently picked up by the media, who uncritically report that climate change has been solved. The result is that it is easier for business as usual to continue. This doesn't mean we shouldn't try to restore kelp forests and to increase their area as much as possible. Rather, that I am sure that a single scheme alone will not work, so that we will have to use a patchwork of smaller marine and terrestrial schemes. Above all, we must do no harm. If left undisturbed, organic carbon stored in marine sediments can remain there for millennia, but disturbance of these carbon stores releases some of the stored carbon, increasing ocean acidification and reducing the ability of the ocean to reduce the rate of increase of the concentration of atmospheric CO2. Thus, protecting the seabed is vital. Enric Sala et al. Estimate that bottom trawling releases 1.47 gigatons of carbon dioxide per year, which is equal to about 15 to 20% of the CO2 absorbed by the ocean annually, and is comparable to the global annual carbon loss from terrestrial soils caused by farming. What should we do? Stop all dredging and stop all bottom trawling and carry out as much ocean afforestation as is practical, and become far better stewards of the land, because the land and its ecosystems are part of and connected to marine ecosystems. I know this will be difficult, but it will be easier than asking ourselves how to live with grace in a dying world.